No.
Assalamu alaikum, girls. Good afternoon.
How are you, Miss?
Alhamdulillah, I'm fine. I'm waiting for all of you to join. How was your weekend, girls? Did you study?
Yes, Miss.
Miss, there is nothing else rather than study.
Exactly, dear. As we cannot go out and it's also Ramadan time. So when we are staying at home, only we can study and pray. Lots of nafil prayer we can do that. Okay, that's
Assalamu alaikum, Miss.
Walaikum salam.
Mohit.
Okay. I can see. Okay. And you know, girls, that this is the second week of Ramadan. We are having the class, and then we have another week. So 3 weeks we have in Ramadan the class. So means the school is going to be this class, online class will be off. I think at the 15th of this month. Okay, so we'll be having 2 more weeks to have class. So by the time, hopefully, I will be able to complete the syllabus. Then I'm planning to go with the paper 4 first. Then I'll go for paper 2. Okay, just like before I did with you in the class, I have to do it like that. Okay, I just need you because it was a huge sound.
Miss, could you repeat about that exam thing you said? I couldn't hear you.
Okay, we said that after completing the syllabus, of course, after the Eid al-Fitr vacation, 31st May, the school is going to reopen, and hopefully that time we'll continue for some past paper as well, and then we'll be having some online evaluation. Because as you know that we cannot have final term exam this time, so we'll be having online evaluation. I will let you know at times that how we are going to have it. But make sure, as I told you before also, presence in the class is also one of the criteria that we are going to consider during making the result of the evaluation class. Okay, so make sure that you are attending the class almost all the time. Even if you have some problem, also just be in the class and listen to the teacher, because it's really very important for you to attend all the classes that we are going to have. Okay, fine, guys. Now, if I remember, in my previous class, in the last week class, I have finished with you mentioning the specific latent heat of vaporization. Do you remember, guys? How many of you have gone through all this topic? I have finished in that much, isn't it, girls? Okay. If it is to that much done, so I want you to tell me, do you have any doubt in any topic from the beginning of this lesson 7 that we're doing now? Do you have any doubt or any thing that you didn't understand clearly? You want me to repeat? Do you have?
Miss, could you explain again the latent specific heat and the latent
Is it like the difference between latent heat and
specific latent heat?
Okay. Now, first, if I start explaining to you what is a latent heat, we say that it is the amount of heat needed for a substance to change its state without changing the temperature. Means the temperature, whatever it will be there. Think about, if I give you an example, that we have 0 degrees Celsius of ice and I want to make it 0 degrees Celsius of water. So we have to provide some of the thermal energy to it, which will allow it to change the state, but the temperature will remain 0 degrees. So 0 degrees Celsius of ice will become 0 degrees Celsius of water. Amount of heat needed will be known as the latent heat. Okay. But if I say that I have 0 degrees Celsius of ice and the amount is 1 kg, then the amount of heat is needed to convert it to 0 degrees Celsius of water will be known as the specific heat capacity. So, sorry, specific latent heat of fusion. Why that word specific came? As I told you before, when you are taking the substance in unit mass, that is 1 kg, then it will become specific. But when it is just any mass, then it will become latent. I hope it is clear for you, Sunny?
Yes, miss.
Okay. So, guys, if nobody else is having any doubt, I want to go to heat. Yes, dear?
Miss, can you explain the specific latent heat of vaporization?
Vaporization. Okay. Specific latent heat of vaporization is the amount of heat needed to make 1 kg of water of 100 degrees Celsius to become 100 degrees Celsius of gas or water vapor. The amount of heat needed will be known as the specific latent heat of vaporization. Okay, so here only one thing is changing, that is 100 degrees Celsius of 1 kg water is becoming 100 degrees Celsius of 1 kg water vapor. If I can measure, I will get the same mass because there will be no change in mass. Only the state will change, but the temperature will also be same. If you remember, here we have discussed one more point here, that is whenever we change this type of state, there what happens over there? Potential energy increases, kinetic energy remains the same. Because kinetic energy is denoted by the temperature of a substance. As the temperature is not changing, so the kinetic energy will remain the same. But as the state is changing, we have to say that the potential energy is increasing. Whether it is solid to liquid, liquid to gas, or gas to liquid again. Means whether it is latent heat of vaporization, latent heat of fusion, or condensation, in all the cases, we are going to have a potential energy which is getting increased, but the kinetic energy will remain the same. I hope now it's clear. Now, I think the rest of you don't have any doubt, so I want to go to heating up. Okay. Now, let me tell you guys, once I start solving the past paper, you will see this question comes in paper 4 as a full question, like a full one question, or it comes in paper 2 as a multiple choice question. So you have to give equal importance to all these topics clearly to understand, so that you can solve both the questions very carefully. Okay, guys, let's do it. Now, this heating curve means I am going to take a substance which will be in the solid state. From solid, I will be making it liquid. From liquid, I will be making it gas. And we'll check what is the difference between all these stages and what amount of thermal energy is taken by the substances in this particular change of state. And when it is just changing the temperature, then what happens? What will be the pattern of the graph? All we need to. So first, if you just take, I hope most of you or all of you have already completed learning is drawing and writing the notes in your record book. If you have done that, please keep the record book in front of you so that it will be easy for you to understand my explanation. Okay, let's start. As I say, I am going to make here some changes of state. From solid, I have to go to liquid and liquid to gas. And we'll see what are the changes that is happening and how the pattern of the graphs keeps on changing. So what I did, see, I wrote it clearly here. Ice at minus 10 degrees Celsius. Okay, everybody knows that even we discussed in our previous classes that water is actually having a point, the point we call freezing point. The freezing point is 0 degrees Celsius where water becomes ice and it is a solid. But if you keep on decreasing the temperature, definitely that temperature can go below 0 degrees Celsius. So what we are doing here, we took an ice, a piece of ice, few pieces of ice you can say, or a certain mass of ice, which is having a temperature of minus 10 degrees Celsius. So we'll be taking it and we'll start heating it with an electric heater. And let me remind you guys, without completing the whole procedure, we are not going to change or we are not going to switch off the electric heater. So all through the heating process will be going on in a row. Will not make any differences in the middle or will not drop the heating procedure in the middle. Okay. So what we are doing here, we say that ice at minus 10 degrees Celsius is heated with an electric heater and the temperature of ice is noted every 20 seconds to plot a graph.
Miss, your voice is cutting off.
Is it?
Yes,
Okay.
Miss.
Just hold on, let me check. Okay. Could you just check right now? Could you hear me clearly, girls? I hope
Yes,
it's
It's a
okay.
little louder, but it's still...
Okay, then you have to check with your network. What about the other girls? Could you hear me clearly, girls?
Okay, now I can.
Yes, miss.
Okay.
Yes, miss.
Yes, fine. That's good. Okay. So we said that we are going for the heating process and every 20 seconds we took the temperature reading and we have actually plotted a graph. And if we just look at the graph, I drew the graph in a way that we have a negative value. If you look at it, the negative value means the zero line is in the middle, and below that we have -10 and -20. Okay, girls, I'm not sure whether could you just check the graph that I gave to you? Did I write there -10 and -20? I think the minus is not shown clearly. Could you check the graph? Yes. So all of you below 0, the two values 10 and 20, put minus before it. We are trying to show below 0 degree, we have -10, -20. And above 0, it will be 10, 20, 30, 40, till 100. Okay. So it means that below 0, we have -10 values, means -10, -20. That is the temperature, negative value. And if it goes up, it is all positive value. Okay. Now, if you see the middle line, that is actually the time in seconds. So what I wrote 20, 40, 60, 20, 20 second, I kept an increase. And I showed you there around 160 seconds. Okay. Now look at the graph. If you just look at it, it starts from -10. I hope all of you girls gave minus over there, -10, -20. Okay. It will not be 10, 20. Below 0, it is definitely all minus value. If you go above above 0, those will be all positive values. Below that, it is negative. Okay. So, if you just look at the graph, it was a straight line from -10 to 20, that is the time axis. You can see I gave the name AB. Did you notice, girls? Isn't it a tilted line? It's not it is a straight line, but it is not a horizontal line. Right, girls? I hope all of you have the graph in front of you, then it will be easy. Okay. From there, B to C, it is a straight line, which is a horizontal line. In fact, it is on the top of the x-axis. And if you just look at the temperature there, it was 0 degrees Celsius. Okay. From C, you can see it straight goes up and it goes to 100 degrees Celsius. Did you notice C to D? It's we can say it is a steeper line, a line that is going up from 0 degrees Celsius of temperature, it goes to 100 degrees Celsius. Did you notice, girls, that one?
Yes, miss.
Okay, fine. After that, check over there from B to E, there's another straight line which is parallel to the x-axis. Means it's a horizontal line, straight line. And then means all through this distance or D to E, the temperature is actually 100. It did not change. And after that, I have given some broken line and it is going upwards. Means from here, it is getting actually evaporated. So step by step, all the parts we need to understand. First, I'll be telling you what is happening between A to B. Means it was the temperature of ice that we have taken. It was at -10 degrees Celsius. We started heating this -10 degrees Celsius of ice with an electric heater. With an electric, let me see. Okay, with an electric heater, and then as it is, okay, just one. With an electric heater, we are heating it with an electric heater, and we say that we are checking the temperature every 20 seconds. We did, and we got a line A to B. So we wrote it clearly. From A to B, the ice is warming up, but it is not melting. Means -10 degrees Celsius is becoming -9 degree, -8, -5, like this. It came to 0 degrees Celsius. Means it is warming. The temperature of ice is changing from -10 to 0 degrees Celsius. But it is not melting. You have to remember that. When the temperature changes, change of state is not happening. So we wrote it clearly. They'll ask in the past paper question that what is happening in this part, A to B, what is happening in B to C. Like that, they'll give you the question. So we have to understand the procedure, what is happening. We have to say from A to B, the ice is warming up, but it is not melting. At this stage, the kinetic energy of the ice is increasing. Why? Because the temperature is changing. You'll remember, temperature changes, kinetic energy increases. Here, it is also happening the same. So, the temperature increases. We wrote it clearly that here, the stage, at this stage, the kinetic energy of the ice is increasing and the temperature is increasing too. Because -10 degrees Celsius of ice came to 0 degrees Celsius of ice. So definitely the temperature got increased here. Now check the next part. From B to C, a mixture of ice and water is in the beaker. A mixture because it is getting melted now. And for also, if you just look B2C, this line that we drew, it is on the top of 0 degrees Celsius. Means at this point, the ice will start melting. At point B, ice is starting to melt. So we wrote it here. From B to C, a mixture of ice and water is in the beaker at a constant temperature of 0 degrees Celsius. The potential energy increases and changes state occurs. See, here we are saying because the kinetic energy is not changing, no change in temperature, but the change of state is happening. And the heat we are providing at this stage actually getting used to separate the molecules far apart from each other to go to the next stage, that is nothing but the liquid. Okay, fine. After that, we wrote C. From C to D, we wrote something else. C to D, okay, before that, let me tell you one thing else. Could you tell me what is the situation at C, particularly at the point C? What is the situation of the ice that we took? In which condition is it now at C, point C? They'll ask you this question in paper 2. At C, what is the status of this ice that I took initially? Could you tell me, girls? Look at the graph at particular point C and
Liquid.
it will become completely water, but at 0 degrees Celsius or higher. Yes, correct answer. It will be completely water, means the melting procedure will be over at C and the whole ice will become water at 0 degrees Celsius. Okay, fine. Now from there, we did not, as I told you, that heating procedure will not stop. We are heating. So from there, the heat that is provided, it will take to increase the temperature of water. So we are writing from C to D, the input of heat rises the temperature of water from 0 degree to 100 degrees Celsius. So this is the part where the water is actually taking the heat energy to increase its temperature because it became already 0 degrees Celsius of water. Now from there, the temperature keeps on rising until it reaches to 100 degrees Celsius. Fine. So what we are saying, in this position, then what is actually increasing? Kinetic energy is increasing. So we wrote, the kinetic energy increases at this point and water starts to boil. At which point? D. At point D, till point D, the kinetic energy was increasing, and at D, it reaches the boiling point, that is 100 degrees Celsius, and the water starts to boil. Very good. Now come to the next part. D to E, what is happening? D to E, if you look at it, isn't it all through 100 degrees Celsius temperature constant? Isn't it, girls? All through 100 degrees Celsius of temperature is constant. Fine. So it means that at this particular point, 100 degrees Celsius of water is actually getting 100 degrees Celsius of vapor. The vaporization procedure is going on, change of state. So we are writing the temperature of boiling water stays constant at 100 degrees Celsius. Potential energy increases and at C, potential energy increases and at C, it is completely still. At E, sorry, it's not C. And at E, the last point that I drew there and then I show the broken line means at this particular point, the ice that I have started with minus 10 degrees Celsius of ice is now nothing but 100 degrees Celsius of vapor and it is completely evaporized. Got it now, first? So this is the whole procedure that we need to learn. We started with a solid turned into a liquid, a change of state happened at B to C at that part. From there again, another change of state, that is from liquid to gas, happened between B2. So this is a comparison between the change of state and the increase of temperature of a particular stage of a particular substance. As we started with solid became liquid, liquid became gas, and then finally it's steam. Okay. Now, if we just look at it, next I wrote few things. This 2 point is also coming in paper 4 as a question. They'll ask you, the question will be like this, for this last paragraph, second last paragraph that I wrote here. Yeah? The line CD is steeper than AB. Why? If you just look at, I hope you understand the word steeper, girls. Who can explain to me what do you mean by the word steeper? Amira, could you explain the word steeper to me? Do you understand?
Steeper.
Yes. Because I'm using the word here. The line CD is steeper than AB. If you just look at the graph that
Like
I gave you.
more, like it's more like
Say.
it's more downward than a normal straight line. Like it's
No, dear. No.
Slope?
The slope, you can say, but in case of a steeper line, the gradient or slope is very high. It will be very high because if you just look at the diagram the way I gave you, A to B, it is kind of more tilted to the x-axis. But C and D is more inclined to the y-axis rather than x-axis. Okay, let me give you another point, then you'll understand clearly. Girls, just check A to B. What is the time taken for going from A to B? From my diagram, could you tell me what was the time going there? Do you look at the time?
20 seconds.
20 seconds. Okay. And what was the temperature difference over there? Just 10 degrees Celsius, isn't it? Isn't it?
Yes, miss.
Yes. So 10 by 20 means how much? 0.5, isn't it? Means I'm finding out the slope or the gradient. So 0.5 you got there. Now you come to the other part. From C to D, what is the time taken, girls? What is the time taken from C to D? Look at the graph and tell me. In my graph, the way I gave, it was actually 20 seconds. No, sorry, 40 seconds. 0 to 60 to 80, 80 to 100 I gave you. So 40 seconds. And the temperature rise was 100. So 100 divided by 40. How much it is? 100 by 40. Isn't it 2.5 girls?
Miss, what are we actually doing?
I'm finding out the gradient to show that why CD line is steeper. By the look you can understand, but here I got the gradient 2.5 and in the first place I got the gradient as 0.5 only. So do you think that CD is steeper? As I told you, the one which is having more gradient definitely is going to have a steeper line. Now the question is that they already said that it is steeper. Why it is steeper? We have to explain. They say here, as I told you, the question will be like this. The line CD is steeper than AB. Explain why. So we are explaining now. First, if you look at the diagram, as I say, CD is steeper than AB. Why? Because the specific heat capacity of ice. Now, I think I never mentioned to you this one before, but now I'm telling you, you'll remember this one, and these values will be always given in the question paper. So you don't need to memorize anything. It will be always given. So look at this. Specific heat capacity of ice is less than the specific heat capacity of water. So if water is more, CD is the part where it was water. So because CD portion, as it was water, it is going to be more steeper. That is the point. And what are the values here? See, I wrote it clearly. 2000 joule per kilogram per degree Celsius. This is for ice. 2000 joule per kilogram per degree Celsius. It's ice. And what about water? It is 4200. So you can see almost, not almost, it is less than half as well. 4200, and for ice it becomes only 2000. That is why when it was at the ice stage, it was not steeper. When it became water, that time the line or the graph line becomes more steeper than the previous one. Is it clear, girls?
Yes, miss.
Fine, very good. Let's go to the next part. The last paragraph of, and do remember, girls, the way I gave you the paragraphs, it will be the answer of one question. So make sure when you're writing, even when I was having the class with in the school also, I used to always say, whenever I'm asking you to change the paragraph, do that. Because each paragraph will be the answer of a question. Don't just keep on writing the whole thing as a single paragraph. Then you'll get completely confused. Okay, guys. Now, the last paragraph that I wrote there, the line DE is longer than the line AB. Now, if you just look at the diagram, guys, do you think that DE line is longer than BC line? If you just look at my diagram, what do you say? Does it seem like that? The DE is longer than BC? Is there anyone who can give his answer? Do you think it's longer? By the look at the diagram, does it seem that it is longer? Anyone from the class?
Yes, miss, it's longer.
It is longer. Yes, yes, it is longer. So why is it longer? We have to explain that. Okay, now if the two values that we used here, these are the values already I think we mentioned in our previous classes. where we were explaining about the specific latent heat of vaporization and specific latent heat of fusion. Okay, here the DE line gets longer because that is the part where actually water is becoming water vapor. And the latent heat of vaporization is actually 2.26 into 10 to the power. I wrote the value in general form, but you can convert that into standard form also. So it becomes 2.26 into 10 to the power 6. See, 1, 2, 3, 4, 5, 6. 2.26 into 10 to the power 6. That is latent heat of vaporization. But if we just look at the other value, that is 3.34 into 10 to the power 5 here. So that was 10 to the power 6 and this is 10 to the power 5. So definitely we can understand latent heat of vaporization.
I'm really very sorry, but then my internet got disconnected. Could you please say where you are explaining?
Yes. We are explaining that point where DE line is longer than AD line. Why it is? Okay, let me see here first. DC line is longer than, okay girl, that's a small mistake. Could you correct it? It is not AD line here, it will be DC line. Okay, by mistake I wrote AD. All of you take the paragraph that I wrote there. The line DC is longer than the line BC. It will be DE longer than BC, not AD here. Small mistake.
Miss, it's BC.
BC. The line BC is longer than the line BC. Sorry, I'm getting mistake again. The line DE is longer than the line BC. Okay. So all of you please correct me. The line DE is longer than the line BC. Okay, please correct that one. BC it will become. By mistake, I wrote AD. It's not AD, it is BC. Okay. So, as I said already, you have checked the diagram as well, and you found that it is this DE line that is longer. But why it is longer? As I said, that at that particular part DE, the water was turning into water vapor. So definitely that is the specific latent heat of vaporization, which is 2.26 into 10 to the power 6. But if you compare that one with the latent heat of fusion, that is happening in BC part, where ice was melting and becoming water. There we need 3.34 into 10 to the power 5 joule of thermal energy. So definitely the part where you need more energy, takes more time to heat it, isn't it? Okay, fine. Now, let's go for the this topic. Do you have any doubt, girls, in this particular one that I finished right now?
Miss, can you explain again why is it longer?
Okay. Now, you remember one thing, as I told you, that DE is the line where water is turning into water vapor. And to turn that one, we need 2.26 into 10 to the power 6 joule thermal energy. I gave you in a bracket both the values. Okay. And on the other one, means at the side of BC, that part, we are actually converting ice to water. Means if 0 degree ice is becoming 0 degree Celsius of water. So we need their latent heat of fusion. That is 3.34 into 10 to the power 5, which is much smaller than the latent heat of vaporization. That is why the line BC is smaller than the line DE. I hope it is clear for you now, Raghav.
Yes, Miss, I got it.
Fine. Let's go for the next one, girls. If you just look at the diagram, the next one we have, that is the cooling curve, another curve. And you can understand this one also comes in paper 2 a lot. You'll see lots of questions up there. Now, if you just look at the diagram, the graph that I gave you, of course, these are not the calculated values, means we never measured anything, but roughly we do it. If you just look at the situation, you can understand that we took a substance. Okay. Now, let me tell you, do you know, girls, what is naphthalene? Naphthalene, naphthalene, we pronounce it. Do you know what is that, girls? Anyone knows?
Yes, Miss.
Okay, could you tell me where do we get it and where do we use it actually? And how does it look like?
To prevent insects, like we usually put them inside the cloths.
Inside our wardrobe, yes. To keep the insects away from that. Okay. So of course, we buy it from the super shops and shops, you can get it. These are kind of crystal type of ball. Before it was only white, now we can find different colors as well. So we keep it inside our wardrobe to keep all the insects away from our clothes. Okay. This is called naphthalene. Actually, we use it like that, but it is a chemical product. Chemical, of course, is a chemical in a crystal form. So that naphthalene will be taken. Now here, what actually we are trying to find out? We are trying to check what is the cooling part. Means here we are going to heat something, then we start cooling. While cooling, will there be any change of state? We want to see that. Actually, there will be. That is why we have picked this naphthalene to go through the procedure. What we did, at first, the naphthalene is melted. And how will we melt? Definitely, we are going to heat it. Melted and heated up to the boiling point. Up to the boiling point of this particular material. Now, what happened? The hot liquid naphthalene is then cooled and its temperature is noted every 20 seconds to plot a graph. So the same thing that we did before, every 20 seconds we kept on taking the readings, temperature readings of this cooling one. We're just going to keep it on the table and will not do anything. We'll allow it to keep there, allow it to be there and cool it on its own to the surrounding. And if you just look at my graph, did you notice I gave a point A, which is around like 82 or 83. In between 80 and 85, I gave a point A, capital A. Did you see that, girls?
Yes, miss.
Yes. So this particular point, we can say 82, 83 will be the boiling point. Okay, means as we said, we'll take the naphthalene, we'll keep on heating, allow it to melt, and it should reach the boiling point. And then we'll just keep it on the table, allow it to cool down, and we'll take the temperature every 20 seconds. Then what we found that around, if you just look at the graph, around 75 degrees Celsius temperature, here we'll see liquid and solid. Means at that particular point, we'll see that this naphthalene will start becoming solid one more time. That part, it was liquid. That's why it was a tilted line. Then it became liquid plus solid. And at point C, it became completely solid. And then from C, as you know that 75 degrees Celsius temperature is a very pretty high temperature. So it will keep on cooling down until it comes to the room temperature. So we didn't show more. We don't need to show. Once it becomes solid, CD is the part where it is actually just decreasing the temperature as a solid. So from A to B, that is the part where it was liquid, means we heated it and we allowed it to cool down. So that is the part it was liquid. Then from B to C, when it is a horizontal line to the x-axis, there it becomes liquid plus solid. Two of them together. Okay. And then after that at C, it becomes completely solid. After that, again, we got a declining line, the one which goes downwards, means it is actually decreasing the temperature at this point. Okay. So let us read out what is happening here. The cooling liquid naphthalene reaches its freezing point 75 degrees Celsius at point B on the graph. As I already told you, at point B, it has reached the freezing point. From point B to C, the liquid naphthalene gradually changes back to solid. From B to C, this is the part the change of state is happening. The change of state is happening. Okay. So as it is happening, there it will be just changing the state but without changing the temperature. So we wrote it continues to lose thermal energy in this region. Change of state occurs, but the temperature remains constant. See, this thing we have to clearly mention that the temperature is going to be just keep on changing. No, in this part, the change of state, it was liquid, it is getting liquid to solid, but there will be no change in temperature. At point C, the last paragraph I wrote, the naphthalene is completely solid and its temperature starts to fall in the region C. And it will keep on falling until or unless it becomes nothing but solid. So this whole region, it is going to reduce the temperature until it reaches to the room temperature. Okay, girls? Now, tell me, do you have any doubt regarding this particular graph? Any doubt you have there for understanding? Tell me, anyone is having any doubt in that part? Because before going to the next topic, I want to explain again if you have any doubt. Anyone? Because in your paper 2, you will see they will ask you what is happening at the point AB. or BC or CD. So you need to understand.
Miss, could you re-explain the point CD?
CD, okay. At this point, as we say, from B to C, it was liquid and solid. Means at that part, at the moment the liquid naphthalene reaches upon temperature 75 degrees Celsius, it will start getting solid. Solidification will start in this particular point. And this whole time, B to C, it will keep on getting solidified. At point C, it will become completely solid. You remember this point. B to C, if I say, it will be solid and liquid together. But at C, completely solid. After C, it goes down to D. CD, this is the part where 75 degrees Celsius temperature of solid naphthalene will keep on decreasing the temperature according to the atmosphere. Means if my room is at 25 degrees Celsius, definitely from 75, it will keep on releasing the thermal energy from it and it will keep on getting decreased, the temperature. Is it clear now, first? Okay.
Yes, Miss.
Fine. Done. So let's go to the next topic. Now here we are seeing clearly the cooling curve of water. Okay, guys. Cooling curve of water. It is not the other one. This one you'll get paper. They'll ask you to draw this one in paper 4 and paper 6. We have a paper you'll be doing in grade 9 with me, inshallah. So that time you'll see this one we do a lot in paper 6. But in paper 4, they'll ask you to draw this one and explain. Now, this is a cooling curve, and the previous one, that was also cooling curve. But that one was from solid, no, that one was a liquid, means I took naphthalene, melted it, made it liquid. Then that liquid started decreasing the temperature. It was cooling down. But in the process, in the middle of the process, it got solidified. But here, what we are doing, the way I wrote the cooling curve of water, it is not like the previous one. That was a liquid naphthalene. We started cooling it down. And while we are cooling it, in the middle, it got changed. It changed its status. Means it changed its state from liquid to solid. Then it again got decreased the temperature. But here, as we are taking water, there is no chance that in the middle there will be a change of state. Impossible. Okay. Now, let us see. As I wrote, if you just look at the diagram, and just look at it here, I have drew the previous graph was kind of a straight line graph. Here it is a smooth curve. In fact, in practical life, if we go through like this type of experimental procedure, we'll always get a smooth curve for the water. So in this part, if you just look at it, I have given certain points. I wrote AB, the one which is much more steeper than BC, a little bit less steeper. And finally, we got CD. That is the almost parallel to the x-axis. Okay. So these are the three parts I have divided this whole graph, and I have to explain these three parts in this particular situation. What is happening actually? Okay. First, if we just look at. Welcome back, girls. Did you hear me? Okay. Yes, fine. Let me join quickly so that I can extend this point and take your yes, dear.
After explaining this, can you explain me the latent heat of fusion?
Sure, I'll do that. No.
Thank you, Miss.
Even if I can't do today because only 5 minutes we have in our hand, just remind me tomorrow one more time, then I'll explain to you. Okay? Yes.
Okay.
So, AB is the part I told you, which is actually much more steeper. Right? We said initially the temperature difference between water and the surroundings is more. So the temperature drop is more and the graph line is steeper. Now, let me ask you one thing, girls. Right now, just imagine we are doing the practical in our home. What is the possible temperature in your room? Could you tell me without the AC on? Normally, what?
25 degrees Celsius.
Yeah, 25, around 20, 22, something like that. And we took 100 degrees Celsius of water. That is why we say the initial temperature difference between the water and the surrounding is more. So the temperature drop is more. The more the difference, the more heat loss will be to the surroundings from the water to the air outside. Okay, then we wrote BC. What is the part here? If you just look at it here, B2C is around 45 to 30, around 45 to 30, that is the part. So we are saying The temperature drop decreases as water cools down along with the time. As water cools down along with the time. As we said, the time goes by, the heat is lost by the water to the surrounding, and eventually B2C is the part where the temperature is going to drop less than before. Finally, CD, if you just look at it, the line came out around 22, 23 like this. Okay, roughly you can say 25. So CD is the part. Graph line is almost parallel to the time axis as the temperature of water is close to the surrounding temperature, so the rate of cooling decreases. Means it has already reached the room temperature, so there is very less chance of losing more thermal energy to the surroundings. Okay, guys. Now I will be taking the attendance quickly. Inshallah, tomorrow I will continue from here because I think, Alhamdulillah, I'm done with the topics. What are the topics I need to discuss with you? It is done. So only we'll be going for solving problems and the past paper also we can discuss. If you don't have any doubt. Okay, let me quickly take your attendance first. Help me. Okay, I can see Amira is there. Afsana. Amina, are you there, dear? Yeah, I can see her. Asma is not there.
Yes, Miss, I'm here.
Okay, fine, dear. Just respond, then it will be easy for me too. Mafuza, Nazabin, Mamita, Maria, all of you are here now. Nazia is here now.
Yes, Miss.
Omnia, I haven't seen. Omnia, are you there? I don't think so. She's not here. Omnia is not here. Salmin, Samia Safa, are you there? Samia Safa, are you there? Yeah, I think she sent me a message. Yeah, she's
Miss
here.
Safa is here.
Yeah. Okay, fine. Then I have Sumaya Alomgir. Are you there? Sumaya Alomgir. Are you there? I don't know. I can't see her. Okay, she's not there. Okay, Saida Zahra.
Miss Sumaya Alamgir is here. Miss.
Is it? Okay, fine. And Tanzila. Saida Zahra is not there. Tanzila, are you there? Tanzila. Anyone saw Tanzila? I don't think so. I haven't seen her. Zara Zubair, she's here. Okay. Then Mahmouda, she's here. Jannatul Noor, I didn't see her. Nabila Hassan is here. Rabat, Reem. Okay. Sadia Islam, Sumaya Islam, Sarah
Miss
Khan.
Janitor is here.
Is she? Okay.
Yeah, her name is Sabah Rahman.
Oh, okay. She should put her name. It's difficult to identify. Okay. Sarah Haidar, is she here? I don't think so. Shaima.
Yes, she's here. Miss Sarah Heather is here.
Okay. What about Shaima? Is she here?
No.
Sumaya Riyad, she's here. No, Saida Ishra, Saida Samia.
I'm here.
I know. Don't worry, I'll call. Okay, Sumaya Zahid, are you there, dear? Let me see the message. Okay, yeah, Sumaya Zahid is there. Sarah Zaman, I have seen. Tasnuban, I have seen. Tamanna, I didn't see. Tamanna, are you there? Sarah Hadir, I see.
Yes, Miss.
Okay. And Zara Chaudhary, Shaima came now.
Yes, Miss.
I can see Shaima now. Shaima, when did you join the class, dear? Shaima, speak out. When did you join my class? Shaima, I can't hear from her. But right now I saw her. Please. If you do like this, then you'll be missing the attendance. Later it will hamper your results. Be careful. Join the class at right time. Okay, guys. So today we don't have. Yes, Shaima, what happened? Why are you so late? Did you join in the class before? Okay, fine. Now listen this. So inshallah, tomorrow I want to check this solving problems and the past paper. And as I told you, we have started 2012 onwards. So tomorrow, all of you keep 2012 in front of you. And please go through the whole note today, tonight. Tomorrow you can ask me your doubts. Before going to the past paper, I need to check that as well. Right, guys?
Miss, did you add me in the attendance?
Yeah, of course. I told you this attendance will be needed when we are going to make your final term result. Yeah, Shanna, I know that, dear. I gave you present. I saw you initially. Don't worry. Okay, dear. Let me conclude my class today. Inshallah, tomorrow we'll be having a game. So make sure you are coming on the right time.
Bye, Miss.
I give you time to join. That's why I'm taking attendance at the last. Okay, fine, guys. Allah Hafiz. Stay safe. Inshallah, we'll have class tomorrow again. Assalamu alaikum.
Bye, Miss.
Bye.